Okay, I don't know why the call just dropped. That was weird. Um, okay, maybe my connection dropped or something. Okay, recording. Yeah, everybody join back. Hopefully everyone will join back. Let me see. Okay, hopefully everybody will join back. Yeah. You all still seeing me and seeing the screen, right? I don't know why the call dropped this now. Okay, cool, thanks. Right, so as I was saying, OSPF is a very deep topic. So I tried to touch on the stuff that Cisco highlighted in particular here. And a lot of these we'll go through today. So don't worry if they're looking like weird concepts right now. But you'll hear about and you'll see a lot of things in OSPF that we won't touch on because it is a very deep topic and Cisco didn't include it here. So I don't want to waste your time studying stuff that is not going to be in your exam. Right, so we'll go through all of these things today, and then we're going to describe what is called a first hop redundancy protocol. So Cisco just said describe the purpose of it. So all we're going to do is describe the purpose of it. It is very deep and it has a lot of configuration and verification and all of these things. But all they asked us to do is describe the purpose of it. So that's all we're going to do here. And then to wrap up today's class, we'll start off the fourth section, and we'll go through configuring and verifying inside source NAT using static and pools. So using static NAT and using dynamic NAT or pool-based NAT. So you'll see with all of these things is 10% and it's 9 topics. So we're literally talking about 1% for each of these topics. So you'll see that I'm giving you all the information, but I'm not spending an hour on each topic because it's 1%, and we need to go through all of these topics. So for this, I usually did the labs. So you touched on a lot of these things in the labs already. You also have the OLab folder. And let me know if you want to learn anything more about these topics. Or you can check the textbooks as well. The reason I won't spend a lot of time on these is because it's 10% and it's 9 topics. So it's 1% per topic. I wanted to focus more on the heavier sections, like the 25% section, rather than these small protocols that don't contribute a lot to the exam. They are all important, but Cisco focusing more here, so we have to go with the syllabus. Right, so before we start, just a quick note. Well, seen it on top here. So Cisco has opened up remote testing online. So I'll just put this in the chat. In case anybody actually wants to do the exam, next month. I don't think the exam centers are going to open up anytime soon. So they want you, well, they give you the option to test online if you want to. These are the things they say you need if you want to do the exam online. A quiet, private location, a reliable device with a webcam, a strong internet connection, some special software that they'll give you, and then government issued ID, which will be like your ID card or driver's permit. Now, the reason I would not recommend this is because I have heard stories of people who tried this already, and they said basically they're very strict with it because you could have, they could only see what is in front of the webcam, like you see me right now, and they don't know if you have an X monitor here, if you have a phone behind the screen, if you have a textbook behind the screen, if you have somebody else talking to you in the next room. They're super strict with it, basically. And if you just look away for a second to scratch something or pick up a glass of water, or you're just thinking and you happen to gaze off somewhere, they could potentially disqualify you from the exam for that. And because of that, I am sort of suspicious about it. I don't know if they get better now, but that was the stories I heard. And that's why I always went in to do my exams, because they're not strict at all in the testing center. They basically check you before and they take away everything that you have not related to the exam. And once you're inside, you're inside. You could watch around. You could, if you see a hard question and you do this, that's completely fine in the exam center. But online, in your own room, the whatever examine proctor or examination proctor you get, they could be as strict as they want, because they don't know what you have in your own room. So read the blog, and if you really want to try it, go ahead. It might be better now, I just thought, I'd share the knowledge that I got. And that's why I usually wait and go in to the exam centers. So yeah, so that's that for online testing there. Let me scroll up now. Yeah. Right. Make sure nobody messaging anything. Okay, good. Right, you all seeing the presentation and the pointer, right? Okay, so move a little slow for a while, but should be able to see it. Nice. Okay, so last class we introduced OSPF. So just well, I like to maintain the headspace and what this whole thing is about before we dive in deep into it. So we talked about static routes, and we said static routes are the simplest way to get routes into our router, to tell our router how you want to move traffic in your network. So just watching this diagram, if you want to tell R2 to send certain traffic to R4 and tell R2 to send certain other traffic to R3, a static route is the easiest way to tell that router what to do and to give it some purpose. But the difficulty with static routes is that if you have 10 or 100 or 1,000 routers in your network, like we have routers on the internet, it becomes very difficult to put static routes because you need to put it in multiple routers, and it becomes very difficult to maintain and to scale and to ensure failover and all of these things. So we introduced what's called dynamic routing protocols. So dynamic routing protocols, it could be categorized in a number of ways. You have a number of different protocols. Just to know some, you have OSPF, you have EIGRP, you have BGP, you have RIP. You had one called IGP at one point, I believe. But you have a bunch of them. Now, all Cisco asks us to study in this version of the exam is OSPF. So we're going to be focusing a lot on OSPF and basically nothing on the other protocols. If you want, you can read up on them. But the idea is the same, right? They help us distribute routing information between the different routers on our network. So OSPF in particular now. So OSPF belongs to a class of protocols called link state routing protocols. So just think of routing protocols or dynamic routing protocols. You have two big groups. One is link state, one is distance vector. We didn't even mention distance vector because EIGRP and RIP and those things fall in that class, and they're not included on the syllabus in any way. So we're going to be talking about link state. So all link state means is that you build what is called a database, or a link state database. It is also called a OSPF database. In some, you'll hear some people say OSPF database. And link state routing protocols know the entire map of the network. They exchange messages and they build this database. So they build this compilation of information, and then through that bit of information, they build a complete topology map of the network. So R1 knows how it's connected here. It knows the entire topology or the entire makeup of this network. And that is a characteristic of all link state routing protocols. So we went through the special addresses. So these are important to learn. The two special multicast addresses that are reserved for OSPF. And OSPF revolves around neighbor adjacency. So every two OSPF routers then, or every two OSPF speaking routers, they form neighbor adjacencies. And we'll go into that more today. To form these adjacencies and become neighbors, they periodically send OSPF hello messages to one of these special multicast addresses. So all we're saying is this: you have a router here, you have a link between them, they're going to form an adjacency using this special OSPF hello message. And in that hello message, they're going to include a number of OSPF parameters that will help them form this adjacency and help them build this database. Because that's the whole point of this, right? To build a database and to exchange routing information. Right, so once you receive the message, you go through the process of adjacency formation and you transition through a number of states. So these are the states. We go from down. So down means, we didn't get any hello messages, we didn't send any hello messages, we just there waiting, and we go through all of these states. So if it's a NBMA link, which is a old type of link, but it still exists somewhere, we may go through the attempt state and then init, or we may just go straight to init, and then we'll go init two-way, exstart, exchange, loading, and full. And these are the descriptions of all of those states. So you'll see, how did Cisco test this boy? I think I saw one question once where they said, we in the init state now. If it works, what is the next state we'll be transitioning to? And they ask, they'll give you two-way, and they'll give you attempt, they'll give you down, they'll give you full. So they basically just need to know the sequence of states. But just for general troubleshooting as well, it is good to have a basic idea of what is happening at each state. Because in real networks, you'll see routers become stuck in different states. And you need to know whether that is expected or whether that is not expected, and what you can do to troubleshoot them. So try to memorize these definitions as much as you can and learn the sequence, because you will see the sequence in real routers. You'll see them transition through these different states until they are full. So in most cases, they will transition to the full state. However, they don't always. Right, and we went through the process for selecting our router ID. I usually recommend, and Cisco usually recommends as well, that you set the router ID manually. And today we'll go through the commands on setting that. And that was it for last class. So now we're going to dive in to some more OSPF concepts, and we're going to continue from there. So now let's explore the concepts of designated routers, or DRs, and backup designated routers, or BDRs. OSPF adjacencies are established from one router to a single other router. So they're peer-to-peer. So you can't send out one hello message and have 5 different routers receiving that hello message. It is one-to-one. Therefore, in a network of 2 routers, we need to form a single adjacency. So one router to one other router, they have one adjacency between them. In a network of 3 routers, we need to form 3 adjacencies. So it's not linear there, right? With 3 routers, think 1 at the top and 2 at the bottom. And think of a side in a triangle now, like when we did spanning tree. So this router here, the router at the top, needs to talk to the 2 routers at the bottom through those 2 links, and then the 2 routers here need to talk to each other as well. So there are 3 adjacencies in total there. And then with 4 routers, you go to 6, and there's a formula. But the formula is not too important. The important thing here is that as we add more and more routers to our network, our adjacency formation kind of looks exponential. Well, our number of adjacency formations. So it does not scale very well. So basically, as we add more and more routers to our network, we start to form too many adjacencies, and the network starts scaling poorly. So to overcome this, OSPF elects a designated router, or DR, and a backup designated router, or BDR, on broadcast links like Ethernet. Routers in an Ethernet segment then only form full adjacencies with the DR and the BDR, and remain in a two-way state with the other routers. And the other routers are called druthers. So those are just states that we need to memorize: designated router, or DR, backup designated router, or BDR, and druthers. So those are the 3 states. So this is what we're talking about here, right? We have an Ethernet segment here. So you would have heard me mention this as like a network or a subnet before. You have a switch, and everything connecting to the same switch is in the same subnet or in the same network. So as I mentioned before, if we had to do full OSPF adjacencies here, this guy would have had to pair with this guy, and this guy, and this guy, and this guy, and all the other ones would have need to do that as well, which is very inefficient. You have too many adjacencies being formed here. So what we do is that you elect the DR, you elect the BDR, and then all the other routers only pair with the DR and with the BDR. So that's what these arrows showing here. So this guy pairs with him and pairs with him. This guy pairs with him and pairs with him. This guy pairs with him and pairs with him. So you'll notice they don't pair with each other here. And as this scales, as you connect more and more routers here, this becomes a lot more efficient because you save on all of these pairings here. So the designated router, or DR, represents the Ethernet segment or the Ethernet network. So the subnet that all these routers using across the switch. The DR represents that segment to the rest of the OSPF network. So everybody outside of this network here, all the other routers in the network, the DR represents this segment to them. So it kind of speaks on behalf of them. So the BDR also forms adjacencies with all routers on the Ethernet segment and exists as a failsafe for the DR. If the DR fails, the BDR will continue passing traffic using the existing OSPF adjacencies. So theoretically, we could have gotten away with just all the routers here pairing with the DR, and that's it. So basically, this DR would have acted on behalf of all of these guys, and he would have exchanged routes with everybody else on the network on behalf of all of these guys. The problem with that is that we introduced a single point of failure. So if this guy goes, this whole network kind of disappears from our larger network because this guy went off until somebody else could be elected the DR, and that whole process will take a while, and we'll go through that process. But you'll see the whole process takes a while. So as a fail-safe or as a backup, we elect the backup designated router, which is why it's named like that. So if this guy goes off, this guy is already paired to all of these guys, and he could take over instantly. Because he already has those pairings. He doesn't need to go and negotiate all those states we went through and all of that. He already has those pairings in his database. So routers become the DR and the BDR using an election process. So this is the problem, right? The election process takes a while, which is why we need the BDR. So the router with the highest OSPF priority becomes the DR, while the second highest priority is given the BDR title. So we have this thing called OSPF priority now, and we're saying the router with the highest OSPF priority will become the designated router, and the one with the second highest priority is given the backup designated router title. And you have additional rules for breaking priorities here and stuff, but usually we assign priorities and we get the DR based on that priority. In the case of priority ties, the router ID is used as a tiebreaker. So higher router ID is preferred. So just, if you leave all your priorities by default, the router ID will be used as a tiebreaker. We can also set a priority of 0 to ensure that the router never becomes the designated router or backup designated router. So just as before, for practical purposes, if you have like this guy in the corner here, if you know he buys somebody's foot or his power plug is real loose, so he's a very tiny router and he might fail at any day, you might want to put him with a priority of 0 to make sure that if he goes, he only takes himself or any downstream networks with him. He doesn't take away this whole segment. So to set the priority for the DR election, they use this command. So you go config T, and then you go into a particular interface. So remember, we will need to go into like this interface here or this interface here and set a priority per interface. So we go in that interface like int FA0 or int GI01, and then you'll see that config-if for interface come up, and then you type in the command IP OSPF priority and the number of the priority. So the default is 1. So if you don't set anything, this will be IP OSPF priority 1 by default. And the range is from 0 to 255. So 0 means the router is a druther, which we just said basically it doesn't take part in the election. It doesn't do, it can't become the DR or the BDR. It'll become a druther. And 255 means, it's the best chance of it becoming a DR because it's so high. Remember, this election process only occurs on broadcast links like Ethernet. So all Ethernet links are broadcast links by default, but they can be changed to point-to-point links for OSPF using the command IP OSPF network point-to-point. So that's the command you enter in there, right? Just like you enter in this one, IP OSPF priority number, you enter in IP OSPF network point-to-point. This allows us to bypass the DR election and speed up the adjacency formation. So I really like this command. This one, because you'll realize this topology isn't as popular anymore. Usually people just connect routers directly, but they connect them over Ethernet links. So people don't use serial links anymore. They usually use like 10 gig Ethernet links or 40 gig Ethernet links. And with this command, IP OSPF network point-to-point, we don't need to go through this whole DR election. We just get a OSPF adjacency like that. So I really like this command. So, however, note that both sides of the link must match before an adjacency will form. So you can't just put IP OSPF network point-to-point on one side of your link. You need to put it on both sides on your router. And obviously, if you have a setup like the one we just showed, where you have multiple routers connected over a switch, you can't put this because it's not a point-to-point link. It's not one point to the next point. It's a point to multi-point. You have multiple routers connected over this link. So some links are point-to-point by default, like serial links, And we can verify the link type using the command show IP OSPF interface and then the interface name. So show IP OSPF interface GI01 or show IP OSPF interface S0-1, S0/1. So this is what you'll see on the output. You see up and up, IP address, process ID, router ID, network type, point to point. So this is what we're looking for here, right? So it's a serial link, so you expect it to be a point-to-point link. What else important here? We didn't. All right, so neighbor count is 1, adjacent neighbor count is 1. So this is what we just went through, right? Adjacency formation. And we'll go through the hellos and the dead timers in a bit. Yes, so hello 10, dead 10. Those are intervals. So it means this router is going to send a hello message. So remember that OSPF hello message that is being sent every 10 seconds. And the dead timer is 40, which means if you don't get a hello back from your neighbor in 40 seconds, then consider him dead. So there's an example here. So show IP OSPF interface, and you see, up and up. That's the interface name there, the process ID. So this is just like the OSPF process. It's not too important, but we'll go through the setup in a little bit. Router ID is important, so we went through why the router ID is important. It acts as a unique identifier on the whole OSPF network, and it helps break ties. Network type again, hello timers, dead timers. So you see here we have a designated router ID, and no backup designated router on this network. So right, because this network type is broadcast, so you see here this network type was point to point. So we didn't see any mention of DRs and BDRs, because you don't do those elections on point-to-point links. But you see here, this guy was broadcast. So we have to do this election on broadcast links. And you see, we elect a DR and the designated router ID is this. So that's us here. And we have no BDR on this network. So the only reason we mention in DRs and BDRs here is because this is a broadcast network. And then, of course, you have loopback interfaces with special network types as well. But they are loopback interfaces. They can't really form adjacencies across them. Now, another important OSPF concept is the idea of OSPF areas. Every network that we advertise in OSPF is associated with an area. OSPF networks always begin with the backbone area, so area 0 or area 0000. In single area OSPF implementations, all networks are included in area 0. However, for very large networks, the LSDB for this single area design may become too large for small routers or layer 3 switches. So in a lot of implementations you go in, you will see, well, you'll always see people start with area 0. That is a law. It is actually in the standard for OSPF. So you'll see somebody, the advanced engineers debating, whether you need to have area 0 or whether you could start with area 1 or something. For our intents and purposes, just start with area 0. That is a Cisco recommended design. And when I checked the RFC, they did say area 0 needs to be a starting area. So when you see backbone area, just think area 0. And when you have something called a single area OSPF implementation, it means that every network that you advertise in OSPF, you just put it in area 0. And you'll see in the command, we actually put that area number in the command. The problem with this is for very large networks, the LSDB or the database for this single area becomes too large for smaller routers or smaller layer 3 switches. So remember, all of this database information needs to be stored somewhere, right? Just like a real database, we need to store this information on some type of memory. And if this database becomes too large, the smaller routers or the smaller layer 3 switches just can't handle it. So they have problems with OSPF convergence and forming new adjacencies and getting all the routes and all of those things. So in such cases, engineers may choose to implement additional areas for the OSPF network. So the most important thing that happens when you create a new area, so for instance, if you start with area 0 and you create area 1, the most important thing that happens there is that you create a new LSDB. So each area creates its own LSDB or own database. And of course, if we have a ton of networks in area 0, and then we create this new area 1 just for a small router, then that small router only needs to learn the networks in area 1. So you could keep area 1 very small. The other advantage is that certain LSAs are filtered between different areas. So the LSAs are just like messages that are exchanged in OSPF. They are link state advertisements. So they are how OSPF advertises different links and different networks into the database. So certain messages are filtered between different areas. Now, area borders also provide useful summarization points for routes in the network. This is real advanced stuff now, and this is why I was saying OSPF could get very deep. And this is literally CCIE level stuff. So what you do is you have your area 0, which is like your central network, and then if you have a small router in an office somewhere, you could say, okay, small router, you have a bunch of networks here, but I don't want you to care about that. All I want you to say is between area 1 and area 0, anything for the 10.0.0.0/8 network, send over to this next router here, and that's it. You don't need to worry about the tiny /30s and /29s and /24 networks and stuff in here, because that'll just kill your CPU and kill your memory. So all you need to know is that I have a summary route to say anything going to the whole 10 network, send to here. So that's multi-area OSPF, and you can see how it becomes very complicated. So that's why Cisco specifically said configuring single area OSPF v2. So they wanted to just focus on single areas for now. So we will only be dealing with single area OSPF for the CCNA exam. But the old labs folder has some of the multi-area stuff. So if you want to mess with that, feel free to go and try it. Now that we've covered a lot of the theory on OSPF, we're ready to try our hands at configuring it. We first begin with the command router OSPF and process ID. So the process ID is just a special number that needs to be unique for different OSPF instances or processes on our router. So realistically, what you're going to type here is router OSPF 1. That's it. Just keep this fixed. You could put 2 and 3 and 4, 10, 100, whatever it is. But in most implementations, people type router OSPF 1. Just to start off, just type 1 there. Once you're in the OSPF process, we use the command router ID, and then you put your router ID here to configure our identifier. Note that this should ideally match an IP address on a loopback interface on the router. So we went through this. I believe there was a question about this in the last class, why we put this as a loopback interface, and the answer is just for stability, right? So usually what we do is we put a unique public IP on the loopback interface, and we put router ID and whatever that unique public IP is there. So now we have our OSPF process, and we have a router ID that we set manually. We then enter multiple network commands to match the networks that we wish to advertise through OSPF in the form network space IP address space wildcard mask space area and the area ID. So I have a whole slide on wildcard mask, so we'll go through that in a little bit. The IP address here is your network address, so your subnet address or your network address, and this is the same thing we would have put in like a static route, right? So if you wanted to go, for example, to 192.168.1.0, we would have put IP route 192.168.1.0. In this case, we are advertising our routes. So for example, if we have a directly connected network, so a fiber or Ethernet, a patch cable connected to 192.168.1.0 on our router, and we want to tell all the other OSPF routers that we have access to that network, we put network 192.168.1.0 and then the wildcard mask corresponding to the subnet mask for this network, and then space area, so the word area, and then we put 0 because we always start off with area 0. So single area OSPF 2 means this will always be 0. We then configure our passive interfaces to prevent OSPF adjacency formation on particular interfaces using the command passive interface and interface name. So just as an example, on your loopback interface, you're not going to form any adjacencies there, right? So you could put passive interface LO0. If you have a network going to an open area, let me say you have an office and you have a router, well, an interface connecting down to that office, and you have no routers there, and you never want to exchange OSPF information down to that office, you could put passive interface and GI01, for example, if that's the interface going to that office. And the whole reason for that is for security and stability, right? So somebody could theoretically bring a modem or bring a rogue router into the office, and they could OSPF pair to your router, and they could disrupt your whole network like that. And to prevent that, you want to put passive interface and make that interface passive. So you will never send those special hello messages through this interface. So the wildcard mask now. The wildcard mask is used to match classless networks. A wildcard mask of 0000 is used to match an IP address exactly. A wildcard mask of 255.255.255.255 is used to match all IP addresses. Think of the wildcard mask as the inverse of a subnet mask. In fact, as a rule of thumb, to calculate our wildcard mask, we take the number 255.255.255.255 and subtract our subnet mask for our network from it. So just as an example, if the interface that we want to advertise or the network that we want to advertise is 192.168.1.0/30, which converts to this with the subnet mask 255.255.255.252, our network command becomes network 192.168.1.0 0.0.0.3 because we took 255.255.255.255 and we minus this number from that. So you get 255 cancel now, 255 here, 0. Same thing here, 2 255s, get 0 again. Same thing here, 2 255s, you get 0 here again. And then 255 minus 252 is 3. So you get 0.0.0.3 as your wildcard mask. And you put your subnet mask or your network address here. Then you put your wildcard mask and then area, which is the word area, and then 0. For single area OSPF, it is always 0. Yeah, I hope that makes sense. Let me know if you need more examples or anything there. But basically the rule of thumb is take this number, so this number is fixed, and take your subnet mask in dotted decimal notation and minus that from that fixed, all 255s there. And that is how you get your wildcard mask here. So put in your OSPF command. So your command will be network this, and this. Okay, let me see how I could do a next example here. All right, let me just add it in here. Right, so let me say we want to, okay, now let me do the 192. Let me say we want to do 10. I'm just going to pick a random network here, /24. So let me say this is our network, right? So just as an example, this is the address that we have on our router. So we have 10.0.1.0, that is the network in our office, and the gateway for that network is 10.0.1.1, and that is the gateway sitting on this router. And what we want to do now is to advertise this office network to our OSPF network. So we go through the other commands before, so we go through router OSPF1, put our router ID, all of that stuff, and what we're interested here is advertising this network, right? So what we want to do is we want to get this command, literally this command that we want to type in, we want to get this command to type in into the router. So the first thing to do is to get the network address and the subnet mask for this network. So we go here, network address becomes 10.0.1.0 255.255.255.0. Yeah. And this will all be subnetting, right? So converting from this to this should be fairly straightforward by now. So this is just 24 ones from the left, and 24 ones from the left gives you all these 255s and gives you a 0 there. And then you do the binary AND thing. Remember we did a binary AND thing before, and we did a binary ANDing between this IP address and this subnet mask, and we get our network address. So because it's a /24, it's fairly easy. That is just 3 255s and 1 0. And when you do the binary ANDing, this thing will become 0 because it is 0 here, and all the other numbers will just be copied across because it is 3 255s. And now we're taking it a step further, and we're saying to get the wildcard mask from this subnet mask, we take this fixed number. So this is always going to be 255.255.255.255, and then we minus in our subnet mask. So this subnet mask for our network, we minus in this from this. So we get 255 minus 255 is 0, and then same thing again, 255 minus 255 0, 255 minus 255 0, and then 255 minus 0, that 0 there becomes 255. Yeah. So that last 255 minus this last 0 here. And then we minus the subnet mask because we don't care about the subnet mask in OSPF configurations. And we have to remember the syntax for the configuration now. So it's the word network space, the network address, which is this was the network address, and then the wildcard mask, which is what we just computed here, 0.0.0.255, and then the word area, and then 0. In single area OSPF, it's always going to be 0 here. Yeah. So now if we get there, I could do a whole video on it if we need to. But the general idea is you take this fixed number, you get your subnet mask in dotted decimal notation, and you minus your subnet mask in dotted decimal notation from this number, and you get this wildcard mask. And then you plug it into your command, network address, wildcard mask, area 0. And that's it. Right, wait, to go back this thing. Right. So our configuration would thus resemble the following. So all we did so far is we went config T, and then we type in router OSPF1. So this 1 here is the process ID. So that's a common Cisco question as well. What does this number here represent? So this might be 10 or might be 250 or whatever it is. Whatever number you have after the word router OSPF, that is your process ID. It's nothing else, not your router ID or anything. It's a process ID. Then inside here, you get into our next submenu, which is why I indented it a little bit here. And you put in the word router ID and your router ID that you set up, which should hopefully match your IP address on your router. And then you start typing in all the network commands. So network address, wildcard mask, area 0. Network address, wildcard mask, area 0. And what this does is it advertises networks that we have connected to this router to the rest of the OSPF network. So it tells all the routers, hey, I have a connection to this network. If you see traffic or you have traffic destined to me or destined to these networks, send it back to me. Now, just with this, with no passive interface commands, this command actually does two things. So it advertises the network to all the other routers, and it tries to form OSPF adjacencies across this network. So just as an example, remember when I said we had an office network on this network here? So it would advertise the office network to all the other OSPF routers, but it would also try to form OSPF adjacencies to that office network, which we know is dangerous now. So remember to include passive interfaces to prevent OSPF adjacency formation where we don't want it. So, you know, well, we didn't do sub-interfaces no, because they took out that topic altogether. But just as an example, if you had GI00, so just forget the dot for now. If you had GI00 and you don't want to form OSPF adjacency across that, you type in passive-interface space and the command and the interface name. So Gigabit Ethernet 00 or GI00 or GI01 or GI02, whatever it is. Wherever we don't want to form OSPF adjacencies and we don't want to send out OSPF hello messages because it might have rogue routers somewhere there. Once you configure similar statements on the neighboring routers, you can issue the show IP OSPF neighbor command to see the adjacent neighbors. Once OSPF works, once OSPF works, it's magic. So you don't need to do anything else. Once you type in these commands, OSPF will start transitioning through these different states, and then once it reaches full, it will start exchanging the networks and everything, and you'll just see your routes magically learned by all the routers in your network. You don't need to go and type in anything, which is why people like OSPF. It's very little maintenance once you have those commands correct. So you see here, we have neighbors, we have different priorities, we have different states. So you see here, right, so you can see a lot of important information here, right? So we know what the priority is. The neighbor ID is just the router ID of our neighbor. The state, so we know these states are the different states we went through a few slides ago. So we see this guy is stuck in two-way because he is a druther. So we know this is expected. But for all the other guys who are not druthers, we expect them to be in the full state, and they are. So you see this guy is a DR, this guy is a BDR, and they are in the full state with the DR and with the BDR, which is good. That's what we expect. everybody except the druthers should be in that full state. And we also see full and a dash here, which means not applicable maybe. So we go across here and we see that these are serial interfaces. So it is a point-to-point interface. And as we said, point-to-point interfaces don't need to go through the selection with DRs and BDRs and all these things. So you'll see that dash there. Then this is the address that we had our adjacency with. And this dead time, as I mentioned before, the dead time is just the time after which we will consider this guy dead, which is why it's a dead time. So it's 40 seconds by default. And every time we get our OSPF hello message from the neighbor, this will reset. So you'll see it go 40, 39, 38, going down. And then you'll see somewhere around 30, you'll get a hello message and it'll go back up to 40. If you see it, you might miss a hello message sometimes if your link bad or if your CPU overloaded or sometime. But you have that buffer. You're going to count down from 40. And every 10 seconds, you should get a hello message. So theoretically, in a normal functioning network, this should never go dead. If it's going dead, it means you have a lot of packet loss or your CPU overloaded or something. So this timer just here to help you see if you're missing hello messages from a neighbor. And of course, the interface that we paid to them on. This output gives us several important bits of information. We see the router ID of each adjacent router. This shows us why setting the router ID manually is so important. We also see the priority of the routers, which controls their DR and BDR elections. So we went through that. We also see their state with respect to the current router. For multiple access links or broadcast links, we see which neighboring routers are the DRs and BDRs and the druthers. So we went through that. We also see the dead timer, which is the timer after which a neighbor is considered gone or dead. By default, this is 40 seconds. The dead timer is refreshed every time an OSPF hello message is received from that particular neighbor. The default OSPF hello timer is 10 seconds. Note that although both dead timer and hello timers are configurable, they must match across neighbors for adjacency to form. So in most networks that I've seen, people just leave this as default. I mean, you shouldn't really have much reason to tweak it. But if you tweak it, you have to tweak it across both routers to maintain that adjacency. If it mismatch, you wouldn't get a adjacency being formed. We also see the address and the interface over which the adjacency was formed. So that's this and that. We can verify that we are learning routes via OSPF using the command show IP route OSPF. So rather than show IP route, as we did before, we do show IP route OSPF. So show IP route OSPF, and you see this O here. So this O means that we learn these routes via OSPF. So once you see some O's in your routing table, you know OSPF working the magic, and we get in some routes without having to manually enter anything. We can also check bits of information concerning our OSPF process using the show IP OSPF command. So show IP OSPF, as we run here, routing process OSPF1, router ID is that. This is an area border router, so that's multi-area stuff anymore. Same thing with number areas and area backbone and all of that. That's multi-area stuff. The important part is here, the OSPF1, as I said, was the process. It's nothing else. It's just the routing process for the OSPF process. And the ID is the router ID. Yeah, everything else here is multi-area stuff. To see the configured hello and dead timers for an interface, we use the show IP OSPF interface and the interface name command. So like gigabit 01. So show IP OSPF interface GI00, and you could put a sub interface there, but just figure that part. Show IP OSPF interface and the interface name, and you see it up and up, and you'll see you see IP address there. You see a process ID. So this is the same router OSPF process ID. This is the router ID. What type of network it is, point to point or broadcast. What else? Right. Okay. Hello timer there and dead timer. So it kind of spells it out fair, right? Hello 10 and dead 10. And you see whether it's a DR or a BDR, and we know that this will only show if this is broadcast up here. And the correct next bit of important information here with the show IP OSPF interface command is no hellos, passive interface, which means we will advertise this network to the rest of the network, but we will not send out any OSPF hello messages. As a last note, maximum transmission unit size, or MTU, must match across links for an adjacency to form by default. The MTU is basically the largest unit of information that an interface can transmit. So remember when we went through Ethernet frames, and we said that a frame could fit in so much amount of data? That's what the MTU is. It's just the largest unit of information that an interface can transmit on a single frame. If we wish to ignore this, we can configure the IP OSPF MTU ignore command on interfaces. If we don't match MTUs or configure this command, neighbors will remain in the Xstart mode. So they will get stuck in this special Xstart mode. And this is a very common occurrence. You'll have switches from different vendors having different MTU sizes by default or implementing MTU differently. And because those messages have a MTU mismatch, they'll become stuck in Xstart. We can use a special debug mode command to check for errors in adjacency formation, which is debug IP OSPF ADJ. So like adjacency ADJ. So look at it here. So it's not in the command mode, just in the privileged exec mode. Debug IP OSPF ADJ. Tell you events debugging is on, and you'll see these special messages now. So OSPF receive DVD database description packet. Just like Google these things. They'll give you a bunch of different technical terms here that you wouldn't know off your head. But you can see where you receive it from. You can see what interface you receive it on. So some things you'll kind of know, some things you won't know. Like I don't know what this sequence in hex is. I don't know what this options means. These things you usually just Google. You can't memorize everything. But you can see this one kind of making sense. OSPF neighbor has larger interface MTU. So we know something going to come up there, right? Once you have a MTU mismatch, you're not going to form that adjacency. So these debugging events really help. So that's it for OSPF. We should have done the lab already. The old labs has a lot more in-depth stuff on OSPF. So let me know if you want any more. But don't go into too much depth because it is a very deep topic. And Cisco pulled out a lot of the stuff there. Right, so next topic, describing the process of first hop redundancy protocols. Now that we understand routing a bit better, let's move on to redundancy. By now, we all appreciate the value of redundancy in networks. Redundancy ensures that the failure of no single link or component can affect our production traffic on services. Dynamic routing protocols like OSPF include some sort of automatic loop avoidance, allowing us to add as many redundant components as we want to the core network. So we could add, however many routers to our network and link them up however much we want. OSPF will calculate, will run that nice algorithm and calculate a loop-free topology within those different routers. And that's the magic of OSPF. Well, part of the magic. It will run a shortest path first algorithm. So that's why it's called OSPF. Once we set up the commands, it will run this algorithm and it will form, it will do loop avoidance automatically. However, in many edge networks, the default gateway for end devices, so the smartphones and laptops and stuff, that default gateway can only be configured as a single device or a single address. This creates a single point of failure, since all traffic leaving or entering the network has to pass through a single link and a single router. So this is what we're talking about here, right? We could have as many switches as we want here. We could have a bunch of different devices here. So this could be, this is an example here, this could be our sales team. And these are the desktops for the people that literally making the company money. And we have that whole thing running under the desk and through walls and stuff, connecting back to a single router. Because there's no way on a Windows machine you could put default gateway 192.168.1.1 and 192.168.1.2. You can't put two default gateways. So that default gateway is one single address on one single device, and it becomes a single point of failure. So if somebody passes and disconnects this router, all of these guys lose access to the internet. Yeah? So that's a problem. A special group of protocols called first hop redundancy protocols, or FHRPs, were created to alleviate this issue. FHRPs use a variety of mechanisms to allow for redundancy in these first hop routers, ensuring that a failure of these routers does not result in an outage for our end clients. Examples of FHRPs include HSRP, VRRP, and GLBP. So these are just names of different protocols that implement this concept. Each of these FHRPs uses a different method to achieve their goal, but they all aim to remove that single point of failure in their networks. So there's just one example. You could connect two different routers to a network, and you have what's called an active virtual gateway. So none of these routers have the actual IP address that these guys are pointing to as a default gateway. They just control what is called a virtual gateway or a virtual IP address. So this guy might have control of it normally, and all the traffic will flow this way. So these guys will go so, these guys will go so, and then if somebody unplugs this, so if this router dies, then this guy will see that this guy dies. You know, he could be saying hello, 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 and then if after 5 seconds he says hello, and this guy doesn't send hello back, he will say, hey, I taken control of this gateway because I don't think you're alive anymore. And then all of these guys will now start sending messages this way. So there will be some downtime, but it will fail over a lot quicker than, you know, running and trying to reconfigure these guys or trying to revive this guy. It'll be in a matter of seconds. So that's the whole process of first-hop redundancy protocols. And again, Cisco didn't ask for any configuration or any specific protocol implementation. They just wanted to learn the purpose of it. So that's the purpose of it there. And these are the different examples of actual protocols that implement it. FHRPs or first-hop redundancy protocols are a big group of protocols that achieve this goal. And HSRP and VRRP and GLBP, these are the actual protocols that do something to get this bigger goal achieved. Right, so that was it for section 3 there. And as the last thing for this class, we're going to start off on one of those mini topics in section 4, which is configuring inside source NAT. So now let's move on to a new section entirely to move away from routing on the whole, which is section 3, and discuss some other useful network services. So that's the whole of section 4, network services. Although the situation has remained largely hidden from the public, the massive growth of the internet has caused tons of issues for us network engineers. One of the largest problems related to the exhaustion of global or public IPv4 addresses relates to the exhaustion of global or public IPv4 addresses. You may have come across public IP addresses if you have ever worked with servers, DVR systems, or even some online games. Basically, public IP addresses are needed to communicate over the internet. Once upon a time, these public IP addresses were handed out in massive blocks to a wide variety of organizations, resulting in our shortage today. So you'll see graphs like this all over the place if you go looking. Basically, this is our IRR address pools. So basically, these are the big pools that the regional internet registries had to hand out to organizations and service providers and everything. So you see, since 2013, we started dropping, and basically different registries ran out at different times, but they all basically ran out by now. So we somewhere here at this point. We after 2020, and I can tell you it's very difficult to get public IP address space right now because we just handed them out. In order to conserve public IP address space, many ISPs now use a technique called network address translation or NAT to allow multiple residential customers like you to share a single public IP or a pool of public IPs of F. Basically, your end devices and modems are configured using private IP addresses. So we went through the different categories and the different big blocks that we have for private IP addresses, right? All the addresses that I talk about, like the 192s and the 10s and the 172s, those are private IP addresses. When your end devices try to communicate out to the internet, these private addresses are mapped to public IP addresses, which are then allowed to talk to other hosts across the internet. In Cisco world, this is called inside source NAT. So it's called different things in different vendors, but Cisco calls it inside source NAT. So to begin, let's start with a simple static inside source NAT mapping. With static NAT, we assign a fixed mapping between a private IP and a public IP using the command IP NAT inside source static. So kind of long command, but IP NAT inside source static, we just type in those exact words, and then we put our private IP address first, then space, and the public IP address. Once the above command is entered in the global config mode, we must then go to the inside interface. So the inside interface is the interface facing the host to the private IPs. So that's your smartphones and desktops and printers and all those things. That's the inside interface. And we use the command IP NAT inside. So just as an example, we go into config T and we put this in config T, and then we go int GI01 if that's the interface facing our desktops and stuff, and we put the words IP NAT inside. Just those commands exact. Then we go into the outside interface facing the host where public IPs are needed, and use the command IP NAT outside. So this might be your interface connecting to Flow or connecting to the Digicel or TSTT. So like int GI02, you go int GI02 IP NAT outside. We can then verify the translation using the command show IP NAT translations. As we said before, you just do the exit out config t because you can't run show commands in config t easily. And then you'll see the translation show up here. So this link has a lot more in-depth definitions, but these are the commands you need in summary. So this is what we're talking about here, right? You have a server, so this could be like a Google server or something that needs public IP addresses to talk, because you can't talk to Google servers with a private IP. So on your side, you have private IPs because you couldn't get those public IPs. So your network admin or you assign this private IP through your Flow modem or through this router here, and you want to talk to the server. So the only way you can talk to the server on a public IP is to use this thing called NAT. So just as the first example, we're using static NAT, and the command for that is go in config t IP NAT inside source static, and then we put in the private IP address of this desktop. So it might be like 10.0.0.2. 10.0.0.2 is what he has, and then we put in a public IP address. So that's what this router has here. This router has a public IP address 59.50.51. And then we go on the inside interface first. So int FA00. So you see this is the interface pasting the inside here, our inside private network, and we type in IP NAT inside. And then we go int FA01. So that's our outside or public interface here, pasting the internet. And we go IP NAT outside. And once we configure that, we could verify it using the command show IP NAT translations. And you see different interfaces being translated differently. So your inside local address is this guy here. So that's your private IP on this side. Your inside global address is the address that it was translated to. So you see 59.50.51. In this case, we literally said we want this private address to be translated to this public address. So we see the private address here translated to this public address here. And then the outside local and the outside global is the same because this server doesn't undergo any kind of translation. That's a public IP, it stays a public IP, no problem. So you see that and that. But the inside local and the inside global is what the translation actually happened on. So the show IP NAT translations will show us this translation taking place. And this colon and this number here is the port. So yeah. We can extend this static NAT translation. So this was a one-to-one mapping, right? This is literally this one IP needs to go to this one IP. And obviously this doesn't help us a lot, right? Because it means if we have 200 hosts on private IPs, we need 200 public IPs. We can extend this static NAT translation or this one-to-one IP mapping to pools of both private and public IPs. This is called dynamic NAT. So static NAT, dynamic NAT. In this NAT configuration method, we still configure our inside and outside interfaces with the same commands as before. So IP NAT inside, IP NAT outside. That's going to stay the same. However, we now configure a special list called an access control list or ACL with the pool or list of private IPs to be translated. Then, instead of binding a single IP to the inside interface as we did before, we bind this ACL instead. This allows an entire pool of private IPs to share a public IP. So this kind of making more sense now, right? On this side, we will have our desktop, our printer, our smart TV, our smartphone, everything sharing this private /24 network. So we want all of this to be able to talk to Google because we want to access, the Google search engine on all of these devices. We don't want to go and type in this for all these devices. It don't make sense. So we'd go with this dynamic NAT instead. So to begin this configuration, we create our ACL and the pool using the commands IP access list standard. So we'll just type in IP access list standard. I'll put in a name for our list, like maybe private address, a private list 1, private pool 1, my private network, whatever it is. And then we put permit network address, network subnet mask. So once we type in this, we'll get into our next menu, and we type in permit and the network address and the network subnet mask. So in this case, it would have been 10.0.0.0 and 255.255.255.0. Yeah, that's our network. So that's the whole network this time. and the whole subnet mask to tell us it's the whole network. We then configure the public address pool with the command IP NAT pool, and we put the name, so maybe like public list 1, public pool 1, and we put on the same line first public IP and the last public IP. So if we only have one public IP, we put the same thing here and here. If we have a whole /29 or a whole /30, whatever it is, flow, TST2, or whoever give us, we put the first IP and the last IP, and the net mask and the subnet mask. So this will be the subnet mask corresponding to the public network this time. So you see here, this was a /24, and maybe we are allowed to use 2 IPs out of this whole /24. Or maybe we're allowed to use the whole /24. It depends on what the ISP assigns us. And lastly, we configure one more command to link everything together. IP NAT inside source list, ACL name or number. So in this case, we put in a name. So we put in that same name here. If this was my private pool, you put my private pool here. And then pool, and you put in the pool name here. So if this was my public pool, you put my public pool here. So just to show the breakdown here, so we could go in, configure the private and the public interfaces just as before. So int and the int name, IP NAT inside, int and the outside int name, IP NAT outside. So that's pointing to the private side and pointing to the public side or the internet side. And then we go in IP access list standard and private pool 1, just as an example, and permit 192.168.1.0, 0.0.0.255. So that's, I need to recheck that. I'm gonna have to change this to wildcard mask. Let's recheck that. I can't remember offhand. I believe it is wildcard mask for ACLs. Right, so network name and either subnet masks or wildcard masks. I'll have to recheck. And then we go IP NAT pool, public pool 1. So this is our public name. And then first public IP, last public IP, and then the network mask here. So it's literally the word network mask and the network mask that we are allowed to use, or that our ISP assigned us. And then this is the private side, this is the public side, and then to bind everything together is IP NAT inside the source list, private pool 1, pool, the word pool, and then public pool 1, which is the name of the pool. So I know when I did this, it seemed like a bunch of random commands. So do it in the lab and just try and memorize it as much as you could. The good thing is in Cisco routers, you could use the question mark and you'll see the prompt for what the next name is. Else just practice it as much as you could, and now I kind of know it because I just enter the same command so much or so often. But yeah, it is kind of weird and a lot of random words to memorize. Once we've performed some things and generated some traffic to be translated, we can use our show IP NAT translations. So just do show IP NAT translations just as we did before and verify that our pool NAT configuration was successful. So you see inside local again is the private IP address, and inside global is the public address that the private address was translated to. And then outside local and outside global is the public address that we want to communicate to. And in this case, and in most cases, this public address will be a server address and it won't be translated anyway. So this will be the same as this. But the inside local and inside global, this is what we're interested in. This is the private address and this is the public address that it was translated to. I see here and here. So you have the different ports that you can translate to as well. So that colon number is a port. And that's it. So we're going to be doing a lot more of these small services in the next class. You see this very long list gone. Right, this long list is a bunch of different services that Cisco wants us to learn about, but they have the whole long list for 10%. So yeah, we just need to learn that as best as we could. NTP, so we did NAT today. We'll go through NTP and DHCP and SNMP and all of those things. So that's the whole section for just a bunch of different useful features that routers have. Right, so I'll check on the ACL. I can't remember if it's wildcard mask or subnet mask, and I'll change the command there, depending on what it is. Let me see what lab we're on right now. We're on lab 16. Can't remember. Any more questions? 15. Okay, lab 15. Yeah. So try out lab 15 and let me know if you have any issues. And I'll look up the ACL stuff and fix it in the presentation. So just look out for the presentation, and I'll upload the video, and that's it. So yeah, let me know if you have any issues, and I'll see you all next week.